Now let's dive into the central limit theorem, or the BLT of statistics. So the central limit theorem, as just a quick reminder, says that we can actually use the normal distribution when looking at sampling. So regardless of the shape of a population, the sampling distribution becomes approximately normal as n increases. In other words, we can think of this as saying if we repeatedly take independent random samples of size n from any population, even if the population doesn't follow the normal curve, as n gets larger, the distribution of sample means or sample percents or sums will approach the normal distribution. So this is a very powerful theorem in statistics, and it's very interesting because it doesn't matter if the original distribution that we're sampling from is left skewed, right skewed, uniform, binomial, whatever distribution it is, the central limit theorem holds true. And this is an amazing result. It's one of the most important theorems in statistics, and it helps make our lives as data scientists a lot easier. So we can use the central limit theorem in the normal curve to calculate areas just like we did previously when we were looking at regular variables. And we're going to do the analogous thing for random variables. The only difference is that our z-score formula changes slightly. So our standard normal curve is always in z-scores. The x-axis is always standard units or z-scores. And previously, we used the formula z is equal to value minus average divided by standard deviation. But remember, now that we have random variables, our mean and standard deviation of random variables actually have special names, the expected value and standard error. So here I have this kind of, I sometimes think of it as a new z-score formula, but it's really the exact same thing, except instead of average and SD, I have expected value and standard error. So whenever I'm dealing with random variables, I want to make sure to use the z-score formula that says value minus expected value over standard error. But the rest of the process is exactly the same. So let's do this puzzle to see how the central limit theorem helps us answer questions about real-world events. So puzzle 1 says in 100 coin tosses, what's the chance of getting less than 45 heads? And I could figure out all of the ways this can happen, but that would take forever. I could actually draw out the exact probability histogram with the outcomes on my x-axis and the probability on my y-axis, but it would be a lot. And we know that since we're tossing the coin 100 times, the central limit theorem is going to kick in. We can use the normal approximation instead. So I am going to use the standard normal curve to do this. And if I wanted to mark 45 heads on the curve and then shade the area to the left to represent getting less than 45 heads, I need to change 45 out of the unit of heads and into standard units. So my first step, again, just like before, is to convert 45 to a z-score. And my z-score formula is just value minus expected value over standard error. So my value is 45. The expected value, ooh, it didn't give me the expected value.
Uh-oh.
But wait, we're tossing a coin, so we already know the expected value, right?
Exactly.
What is it?
So expected value is going to be, it's going to be 50-50 every time you flip a coin.
Yes.
And you've got how many coin flips?
I've got 100.
100, so we expect to get 50 heads.
Exactly.
Or 50 tails.
Our expected value is 50. And I could go ahead and think about tossing a coin 100 times we know is a binomial random variable. So I could have said my expected value is n times p, n is 100, and my probability of success is 0.5. But if we're doing something like flipping a coin, we can just kind of think about it logically and don't need to bother with the formula. But so I'm going to plug in 45 minus 50. Let's go ahead and use our formula for standard error. So the formula for the standard error of a binomial random variable is the square root of n times p times 1 minus p. So wait, if you could help me out here, I have the square root of 100 times 0.5 times 0.5. Actually, with this one, I think it should just be 5, right?
Yeah, square root of 25 is just 5.
Is just 5, okay. So this problem did not give us the expected value in standard error, but we know about binomial random variables, so we can easily calculate them. And then if I plug that into my z-score, I have -5 over 5, or -1. So what that means is right here on the standard normal curve at -1, this actually corresponds to getting 45 heads. And if I wanted to mark 0, 0 is right in the middle. That's the average or the expected value. So that is 50 heads. So it makes sense that our z-score is negative for 45 heads because we're below average. So that's step 1. Step 2 is to draw my picture. I want to know what's the chance of getting less than 45 heads. So I'm going to shade everything to the left of -1. And then step 3 is to go ahead and actually calculate that area. And I know Wade absolutely hates the normal table.
Yes.
So let's go ahead and use Python. I think this is just a CDF, right? This is just the area to the left of -1.
Yeah, the area of the left of the normal curve to -1 is norm.cdf of -1. And I get 0.1587.
So 0.1587. So that is my answer. If I was doing this in Python, I definitely need to remember to import norms. So I would do from scipy.stats, import norm, and then I can just do norm.cdf of -1. So the answer to this question in 100 coin tosses, what's the chance of getting less than 45 heads? Well, I'd expect to get 50 heads. But the exact chance that I get less than 45 heads is about 16%.
So Carly,
Yeah.
I've got this crazy question. Do we want to see how close this is? Because
Always.
Didn't
Yes.
you? Because you modeled a binomial distribution as a normal distribution here.
Yes, I did. And that's because of the central limit theorem. I said, because we're doing this 100 times, that is 100, I'm saying this distribution is going to be close enough to the normal curve.
So if I have a binomial distribution, I have this same distribution. I can do the CDF in Python of the binomial.
Ooh, yeah.
So this is a binomial distribution with n equals 100 and p is equal to 0.5, right?
Yup.
And if I do a CDF of, I want what the area of the left of 45 is. Is that right?
Yes.
And we get 0.1841.
0.18. So our area.
To the left of 45 of a binomial distribution is going to be 0.1841.
So we were 0.1841. We were close, right? I got about 16% using the normal approximation, and I got about 18% using the binomial distribution.
So what's interesting about the central limit theorem is it says that it's going to be close, and it exactly is close, and it's going to get closer the more samples we take,
As
right?
n increases, yes. And this is actually a really good way to point out that the normal approximation is just an approximation. It's not going to be exact. And we know statistics is never having to say you're certain, and we were pretty dang close here.
Exactly.